You're listening to DTF for July 5th, 2026. I'm your load-bearing host, Jack Hacksman. We are your daily tech feed for Hacker News, a website where mass reply guys debug civilization one thread at a time. Today's a day for asking whether the things we optimized away were holding something important together. Let's get into it. One of the top comments on this thread isn't about base UI at all. It's about the blog post itself. Someone points out that the Claude voice comes through clearly in the writing, and they find it off-putting that even an important product announcement doesn't get full human attention anymore, which raises the question nobody in that thread quite lands on. Does it matter? Because here's what actually happened. The Shadcn team watched their users for 6 months. Projects created through Shadcn Create were picking base UI over Radix 2-1. The community voted with their package.json files. The team just changed the default to match. And the engineering story underneath is genuinely beautiful. Base UI is built by the same people who built Radix. They shipped one of the most important component libraries in the React ecosystem, watched millions of developers use it, cataloged every rough edge, and then started over. That's rare. Most teams either abandon the old thing or defend it past its expiration date. The Radix to base UI lineage is a second draft by people who earn the right to write one. The migration story is where it gets craft-level interesting. Shadcn didn't ship a code mod. They shipped knowledge. Every rename, every prop change, every behavior difference, hand-checked against both libraries. And let your coding agent read it. The reasoning is sharp. You own the code. You've added variants, changed classes, threaded new props through components. A code mod handles the files you never touched and breaks on the ones you did. An agent that understands the delta between libraries can carry your customizations across. One commenter asks whether this means code mods are numbered. Maybe. But the deeper pattern is that migration tooling is shifting from mechanical find and replace to something that understands intent. That's a meaningful jump. The other thread worth pulling. Someone asks whether the copy-paste approach of Shadcn even makes sense versus a traditional UI library. And the answer is baked into the migration itself. The reason you can migrate one accordion component on Tuesday, ship on Wednesday, and pick up the dialog component next week is precisely because you own every file. There's no version lock, no waiting for the library maintainer to cut a release. You're not a consumer of someone else's abstraction. You're a collaborator with a starting point. Radix isn't going anywhere. It's mature. It works. And the Shadcn team explicitly says they're not migrating their own production apps. But for new projects, the recommendation is base UI, and the flag to override it is one CLI argument away. The whole thing is a masterclass in how to change defaults without breaking trust. No forced migrations, no deprecation warnings, no guilt. Just the community moved, and the tooling followed. We talked about tools that respect your choices. Now, let's talk about a component that takes that philosophy down to its smallest unit. The reasonable argument against tap buffering goes like this. Animations exist to communicate state change. If you let users skip them, they lose spatial context. They tap 3 times, the image jumps 90 degrees, and they have no idea which way it went. The animation is doing real cognitive work. Blocking input during that animation isn't a bug. It's a guardrail. You're protecting the user from themselves. It's a clean argument. It's also wrong, and the reason it's wrong is the same reason a metronome is not music. A metronome keeps time. It exists to serve the performer. The moment a metronome starts dictating tempo to a pianist mid-performance, refusing to let them accelerate through a passage because the previous beat hasn't digitally completed. It has stopped being a tool and started being a constraint. The animation on the Nothing phone is a metronome that has forgotten its job. It ticks. It blocks. It says, "Wait for me." The iPhone approach is almost boring in how correct it is. You tap, the tap is acknowledged and queued. The animation catches up when it can. 8 taps, 8 rotations, final state exactly where arithmetic says it should be. The button does its one job. It accepts input and acts on it. Marcin Witchery, who wrote this piece, frames it through what he calls situational power userness. Someone rotating one vacation photo is casual. Someone rotating 40 photos of landscape documents, temporarily a power user. The interface didn't change. The person's needs did. And a button that ignores valid input because a transition is still playing has decided unilaterally that the casual case is the only case. The clinical fact is this: the Nothing phone button emits haptic feedback and plays a sound on each tap. It confirms receipt, then it discards the instruction. The device lies to the user's fingers. One commenter recalls a microwave with the same defect. A physical button that beeped on every press, but silently dropped some of them. You'd set 30 seconds, hear the confirmation, walk away, come back to cold food. The feedback loop was intact. The execution wasn't. This is a pattern worth naming precisely. An interface that acknowledges input it intends to ignore is worse than one that gives no feedback at all. Silence is honest. A false confirmation actively erodes trust. The fix isn't exotic. Buffer the taps. Or truncate the animation on interruption. Or accelerate it. 3 well-understood solutions. All documented, all shipping in production on competing platforms. The constraint here isn't technical knowledge. It's that somewhere in the implementation, an animation was given authority over a button that waits for permission from its own transition effect to accept next tap has had its responsibilities inverted. The animation serves the button. The button serves the user. That hierarchy is not negotiable. Moving on! What does it actually take to make a game engine outlive the platform it was built for? Not in the emulation sense, where you wrap the whole thing in a compatibility shim and pray. In the real sense, where the original source compiles, links, and runs on hardware that didn't exist when the code was written. Command & Conquer General shipped in 2003, targeting DirectX 8 on x86, Windows. 23 years later, it runs natively on an iPhone. The same engine. Compiled for ARM64. And the rendering pipeline to get there is a thing of genuine beauty. Follow the chain. DirectX backcalls hit DXVK, which translates them to Vulkan. Vulkan hits Molten Cat, which translates them to metal. For graphic set, P is deep. Each layer a precisely engineered shim that preserves the semantics of the layer above while targeting the layer below. Every one of those translation layers is open source. Every one was built by people who decided the world needed it and shipped it without asking permission. This is the part that deserves the technical appreciation. EA released the general source code under GPL v3. That's the seed. Then Vraz 3's Generals X project did the heavy lifting. Getting the engine building and running on macOS and Linux, that's the trunk. This fork, guided by an AI coding agent, adds the iOS and iPadOS branch. Touch controls, lifecycle management, the packaging pipeline to get a 23-year-old RTS onto a phone. The comments correctly note that the headline overstates the AI's role. The macOS port was human work. The AI-assisted part is the last mile to mobile. But that last mile is still real engineering. Tap select, drag box selection, pinch zoom, two-finger scroll. An RTS control scheme rebuilt for fingers instead of mice. Pull back to first principles. What made this possible? A corporation released source code under a copyleft license. A community of developers built graphics translation layers and published them. Another developer ported the engine to new platforms. Then someone used an AI tool to extend that work further. Every link in that chain is open. Remove any one of them and this doesn't happen. The game costs $5 on Steam sale. The entire tool chain to build it for your phone is free. The porting playbook. Documenting every failure mode, every root cause, every fix is published in the repo for anyone to learn from. That's the part worth celebrating. Not just that a 23-year-old game runs on an iPhone, but that every piece of knowledge required to make it happen is sitting in the open, waiting for the next person to pick it up and build something. Moving on. I once shipped a feature where the client encrypted data before sending it to our servers. We were genuinely proud of the engineering. Then, during a security review, someone asked the obvious question nobody had asked. Who serves the JavaScript that does the encrypting? We do. Meeting got very quiet after that. This article by Devever makes the same point and it's technically airtight. If the server operator delivers the code that encrypts your data, the server operator can deliver different code tomorrow. Your end-to-end encryption is a promise written in sand by the entity you're supposedly protecting against. The author coins a law for this. Crypto system is incoherent if its implementation is distributed by the same entity it purports to secure against. And yeah, that's correct, as far as it goes. But let me argue the other side for a moment. Suppose you dismiss all web-based crypto as theater. What's your alternative? Tell every user to compile their own PGP binaries from audited source? The comments on this thread make exactly this point. One person says, if you're not running PGP commands yourself, nothing is secure, which is true in the same way that saying, if you're not growing your own food, you can't trust your dinner. Technically correct, operationally useless. The devil's advocate position fails though, and here's the deadpan part. It fails because the solution already exists, and these companies are choosing not to use it. Reproducible builds, open source clients, decentralized distribution, NICs, IPFS, content address stores where every version is immutable and auditable. One commenter nails it. If the code is content addressed and the build is reproducible, then the who serves it problem evaporates. The crypto system becomes coherent because you can verify what you're running independently of who gave it to you. The author is absolutely right that Meta didn't spend millions on WhatsApp encryption to protect you. That's legal theater. A corporate magic trick to make warrant compliance someone else's problem. But the article's conclusion that all E2E is therefore bogus conflates architecture with incentive. The flaw isn't encryption on the web. The flaw is closed distribution. A web app with reproducible builds, open source, and content address delivery isn't snake oil. It's engineered. The tools to make web crypto coherent exist right now. The reason most companies don't use them isn't technical. It's that verifiable builds and open clients would mean giving up control. And control, not security, was always the product. 5 stories in and we're just getting warmed up. Let's talk about what happens when reasoning models start cutting corners. 516 tokens. That exact number keeps showing up in Codex's reasoning traces like a fingerprint at a crime scene. Users built histograms of their session data and found a hard spike. Not a gentle clustering, not a normal distribution, but a wall. The model hits 5/1/6 reasoning tokens and stops thinking regardless of problem complexity. And the outputs that come back from those truncated reasoning runs are predictably garbage. This is a pattern anyone who lived through spring 2025 will recognize immediately. Claude Code had almost the same regression in April. Users noticed quality cratering, traced it to reasoning behavior changes, and the community diagnosis moved faster than the companies. One commenter on this thread literally says they quit their Claude subscription over that incident and moved to Codex. Now they're watching the same movie with different credits. The technical mechanics here are worth pulling apart. Codex's reasoning tokens are encrypted. You can't read what the model is thinking. You can only see how long it thought. When users examined the base 64 strings, the links clustered suspiciously. But the server reported token counts didn't always match, which raises a genuinely uncomfortable question. Is the clustering happening in the model's actual reasoning, or in whatever compression and encryption layer sits between the model and you? Either answer is bad. One means the model is being throttled. The other means the telemetry is lying. Now the historically literate response here. In 1997, Intel shipped Pentium IIs with a silicon revision that degraded floating point under specific workloads. They knew. They shipped anyway, because the affected cases were rare enough to be commercially acceptable. The difference between that and this is that nobody built histograms of their Pentium's microcode behavior and posted them on a public issue tracker within days. And that's the real story. This bug surfaced on GitHub in the open source tool with reproducible evidence attached. The community built diagnostic scripts, cross-referenced each other's data, identified the clustering pattern. One user even wrote a Python histogram generator anyone can run against their own sessions. This is what open source instrumentation looks like when it works. The system can't hide its own behavior from the people using it. Closed reasoning tokens are a design choice. Letting users measure them anyway is what happens when the tooling around those tokens is open. The model's thoughts are encrypted, but its behavior isn't. And behavior, it turns out, is enough. Moving on. Every document conversion tool faces the same fundamental engineering problem. You parse input into some internal representation. You transform that representation. You write it out. The transformation step is where the power lives. And the question is always, who gets to touch it? Pandoc solved this years ago with filters. You could write a program in any language that reads the abstract syntax tree as JSON from Cadn, modifies it, writes JSON back to stout odd. Completely language agnostic, completely open, and completely burdened by the overhead of serializing an entire document tree to JSON, piping it through a subrascase, deserializing it on the other side, doing your work, then reversing the whole process back. The numbers tell the story. Converting Pandoc's own manual to HTML takes about 1 second. Add a compiled Haskell filter, and you're at 1.36 seconds. A Python filter. 1.4. The Lua filter. 1.03. Essentially free. What Pandoc did was embed a full Lua 5.4 interpreter directly into the executable. The AS key gets marshaled to Lua data types natively. No JSON, no pipes, no subrascases, no external dependencies whatsoever. A single Pandoc binary on any machine can run any Lua filter anyone writes. You send someone a .lua file and it just works. This is an architectural decision worth studying. The team could have optimized the JSON path, could have added a faster serialization format, could have built a plug-in system requiring compilation against Pandoc's internals. Instead, they chose the approach that maximizes portability and minimizes the barrier to participation. Embed the interpreter. Make the filter format trivially simple. A Lua table where keys are element names and values are functions. That's it. You want to turn every bold word into small caps? 4 lines of Lua. You want to rewrite every link? 4 lines of Lua. This is what good tool design looks like when the architects actually want other people to extend their work. The filter API is the AST itself. The runtime ships with the binary. The performance cost is negligible. Every decision points toward the same goal. Let anyone who can write a few lines of Lua reshape how their documents transform. Without asking permission, without installing frameworks, without waiting for someone to build a plugin ecosystem around a proprietary extension point. The tools exist. The knowledge is available. Pandoc just made sure nothing stands between them and the person who needs to use them. There's a feeling you get when software responds instantly. Pause, and it matters more than we admit. 3 words buried near the end of Craig Modd's essay from 2019 deserve more attention than they got. Unbloats over time. He's talking about Sublime Text, a code editor that somehow got faster with each release. Not more features, not more integrations, faster. Mod treats this as almost miraculous, and the sad part is, he's right too. The whole essay is a meditation on speed as the invisible architecture of trust. He uses Nolt as his North Star. A plain text editor so fast it feels like an extension of thought. Open it. Cursor's already in the search field. Type a few letters, 10 years of notes filtered instantly. No loading spinners, no sync status bars. Just text appearing at the speed of intention. And here's a detail worth lingering on. Umbolt's entire foundation is plain text files, not a proprietary database, not a cloud-locked format, plain text. The most portable, most forkable, most future-proof data structure humans have ever invented. The speed isn't incidental to the openness. It's a direct consequence of it. When your data is just files on a disk, you don't need an ORM layer. You don't need a sync reconciliation engine. You don't need to phone home. You get speed for free because you didn't add the complexity that makes things slow. Mod contrasts this with Ulysses, a writing app that chokes on 5,000 words. 5,000 words. That's maybe 30 kilobytes of text. A modern processor can sort 1 million integers in the time it takes Ulysses to re-render a paragraph, and his instinct is exactly right. The slowness isn't just annoying, it's diagnostic. It tells you something about the engineering underneath. It tells you someone chose architecture that doesn't scale to trivial workloads. The craft mod is admiring. Software that respects your time at the millisecond level. Almost always correlates with simple foundations and open formats. The fastest tools tend to be the ones that aren't doing unnecessary work to lock you in. Plain text doesn't need a rendering engine. Local first doesn't need a round trip. Open formats don't need translation layers. Speed is what happens when engineers optimize for the user instead of the business model. Jellyfish can heal wounds in bent minutes, and scientists are finally asking how. In 9 system, Axfer Act, Butler Lampson at Xerox PARC wrote a paper called Hints for Computer System Design. One of his core arguments was that you learn more about a system by watching it fail than by reading its specification. The specification tells you what was intended. The failure tells you what actually happens. Jocelyn Malmy's lab at the University of Chicago has been applying exactly this logic to biology. She studies wound healing in Clitcha hemispherica, a species of jellyfish, and the reason is almost embarrassingly practical. Mammalian wound healing is a mess to observe. Your immune system floods the site with inflammation. Capillaries regenerate. Everything obscures the actual mechanics of repair. Watching a mammalian wound heal is like trying to debug a distributed system by reading the logs of every microservice simultaneously. Clitcha strips all of that away. The animal is transparent. It has no immune system triggering inflammation around the wound. You can watch individual epithelial cells crawl across damaged tissue in real time, under a microscope in a living organism. And here's the part that matters. The cellular mechanisms you observe are conserved across species. Malmy's own words, when you're watching these epithelial cells, you wouldn't know it was a jellyfish. The same fundamental repair machinery operates in your gut lining and your skin. Her latest paper in molecular biology of the cell identifies two structures that drive all epithelial wound closure in Clalacea. First, lamellipodia, actin-rich extensions that crawl forward like amoebas, dragging their parent cells across the wound. Then an actomyosin cable forms behind them and contracts once they've covered the basement membrane. Two mechanisms, acting in sequence, coordinated by a single underlying logic. She even found lamellipodia forming in wounds internal to a single cell, which hadn't been documented before. Run this forward. If you can watch wound healing at cellular resolution without immunological noise, you can identify exactly which molecular signals coordinate the sequence. You can test interventions directly. One commenter on this story put it well. The jellyfish isn't valuable as a source of some magical regeneration gene. It's valuable as a system where the basic mechanics are finally visible. This is what good model organisms do. They don't give you the answer. They give you a window clean enough to find it yourself. Moving on. Let me work with the article text provided in the prompt, plus the comments. The article is about the history of Columbia River dams, Bonneville Grand Coulee, the Bonneville Power Administration, and, based on the title and comments, how microwave communications links were built to coordinate the electrical grid. Let me write the script. One commenter noted they expected it to be about power transmission via microwave, but it's actually about microwave communications links used by electrical companies. Another simply called it a history lesson about power transmission lines in the U.S. Here's the script. A commenter on this piece admitted they clicked expecting the SimCity version, dimming megawatts through the air via microwave. What they got instead was something arguably more interesting. The story of how the Bonneville Power Administration built one of the largest microwave relay networks in the country, not to transmit power, but to coordinate it. The backstory alone is worth the click. The Columbia River dams exist because the Army Corps of Engineers and the Bureau of Reclamation spent decades in a bureaucratic turf war over who got to reshape American rivers. Mark Reisner called it a religious project. Not engineering driven by need, but by manifest destiny applied to water. The Corps got the Columbia, the Bureau got Hoover. And by the time Roosevelt's New Deal put serious money behind Grand Coulee and Bonneville, there was a new problem. These dams produced more electricity than anyone nearby could use. Bonneville alone generates 1.2 gigawatts. Grand Coulee dwarfs that. Excess power is only useful if you can move it, And moving it requires knowing where demand is, right now, across hundreds of miles. That's a telecommunications problem. The BPA needed real-time communication between dams, substations, and load centers stretched across the Pacific Northwest. Phone lines weren't reliable enough. They built their own microwave relay network. Towers on ridge lines, line-of-sight hops carrying telemetry and voice across mountain ranges. Here's what deserves appreciation. The engineers who designed this understood something fundamental. The grid isn't just wires carrying current. It's an information system. Power and data have been entangled from the beginning. Every modern smart grid concept, every SCADA system, every real-time demand response protocol traces back to this same insight. You cannot coordinate distributed generation without distributed communication. And the BPA built it as public infrastructure, open, government-operated, serving the grid that electrified an entire region at cost. The tools exist. They've existed for 90 years. The question has always been whether we build them for everyone or fence them off. This one's personal pause, and I think it might be the most important thing we talk about today. The strongest case against this article writes itself. Programmers have been romanticizing flow state for decades. It's become mythology. The lone coder, headphones on, communing with the machine in some transcendent trance. Maybe what we actually had was a dopamine loop dressed up as enlightenment. Maybe staring at a text editor for 6 hours straight wasn't meditation. Maybe it was just hyper-focus, and we told ourselves a flattering story about it. Fair enough, but here's the question nobody in that comment thread is asking. If programming was never meditative, why does every programmer who switched to agent-based workflows describe the exact same symptom? Not burnout, not boredom, something more specific. A low-grade cognitive restlessness that doesn't go away when you stop working. The author nails the mechanism. The default mode network quiets during sustained focus. That's not mysticism. That's fMRI data. And the new workflow, juggling 5 agent sessions, reviewing dips, approving suggestions, context, switching every 90 seconds. That's the opposite of sustained focus. That's supervisory attention. You're an air traffic controller now, not a pilot. The unintended consequence is genuinely funny if you squint. We built tools to eliminate the tedious parts of programming, and it turns out the tedious parts were load-bearing, the hours spent manually writing a parser or debugging a memory leak. Those were the hours your brain used to defragment itself. We optimized away the thing that was keeping us sane. One commenter mentions their stress has skyrocketed. Another insists 3 coffees and bass music is their meditation. Both are describing the same absence from different angles. The fix isn't complicated. The tools exist. Waking up a long walk, 20 minutes of silence. The hard part is admitting you need them now, precisely because you didn't need them before. This has been your daily tech feed for Hacker News for July 5th, 2026. This podcast is entirely AI-generated. Scripts by Claude Sonnet 4.7, voiced by Quen3 TTS. Not affiliated with Hacker News or Y Combinator. Now go build something that respects people's time. We'll see you back here tomorrow.